Hey everyone, this is Andrew, and in this video we're going to talk about logic design. Now, logic design is a course that is in many robotics programs. It's also usually a required course for electrical engineering majors or computer science majors. Depends on the college, and it also might be called something else. But logic design is a common name you'll see for it. So in this video we're just going to go over binary numbers, which is kind of like a fundamental building block in any kind of thing you'll talk about in logic design. Everything you do in logic design, for the most part, is using the binary system. So you really got to kind of get to grips with what it is, how it works, and all the little tiny details. So if you have a normal 10-base number system, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then at 10, the ones column goes back to 0, and then the tens column gets incremented. And it's the same case with binary, except since there aren't the 10 different numbers, it happens every 2, which is why it's binary. So I'll just kind of do some examples here. So 0 in binary is just going to be 0. Now we could also write 0, 0, 0, 0, 0. Same thing as normal numbers where the zeros coming before don't really matter and zeros coming after decimal don't really matter. It's the same way in binary. So now if we want to increase to 1, we do the same thing we do in our normal number system. And we're just going to say 0, 0, 1. So it's exactly the same for 1 as it is in a 10-base system. Now things start getting weird when we get to 2, because what's going to happen is we're going to say 0, but we want to increment this number, but we only have zeros and ones to deal with in binary. So we have to increment this one, bring this to 0. So since we can't do anything else to this because we only have 0 and 1s, it overflows into the next, what is essentially the tens column, quote unquote. It really becomes the 2s column. You know what I mean? So since in our normal number system we'll have the 1s, the 10s, the hundredths. In this case we have the 1s, the 2s, the 4s, the 8s, etc. So that's how it works. So we go into the 3, and here 0, 1 is what we already have. We want to increment it again. 1. We add to the end. Now things get weirder again to us when we get to 4, because now we can't increment this one again. So we're going to overflow into this one, but we also can't increment this one anymore because it's already 1. So we have to overflow into this one. So we're overflowing twice, 1, and then these get brought back to 0. So this is 4. So as you can see here, we have the 2s column filled out for 2, and we have the 4s column filled out for 4s. Now, as you can imagine, this is going to get the same when we go down to 8, so I'll just kind of continue real quick the next few ones. So 1, 0, 1, we're incrementing that column. We're going to add another one. We're going to overflow into this for 6. Now, in an easy way, what you can see here is we have something in the 4s column and the 2s, nothing in the 1s. So if we don't know what this number is in our 10s-based system, we can just say, well, 4 plus 2 plus 0 is 6. Bam. So now we do the same thing for 7, 1, 1, 1. That last one gets incremented. And now we have an overflow issue where we have to add a 4th digit. So if we were working with some kind of weird processor that only had 3 bits, or whatever we're doing, it only has 3 bits, we would be out of numbers at this point. That's not really a concern for anything in modern day, but it's something you should understand. That if you have an 8-bit processor or 16-bit processor and you're doing math, and you need something greater than that, you have to come up with some different way of storing your number. You can't just store it in one place if you don't have enough bits to store it in. It's just the way it works. And we'll cover that, in greater detail in other lessons, but for this, we'll just kind of wash it away. So now we have to add another digit. So these all overflow. We have 1, 0, 0, 0. So as I said before, we have the 2s, we have the 4s, and now we're going to have the 8s. So here, it's a really messy 8, but that isn't 8, I promise. So that's the 8s column. Keep continuing. 1, 0, 0, 1. 1, 0, 1, 0. And if you were to say, what is this number in tens if you didn't know it, we're just going to say, we have something in the 8s column, plus nothing in the 4s column, plus something in the 4s column, plus nothing in the 1s column. Sorry, I said that a little weird. Let me fix that. It's actually supposed to be a 2. So we have something in the 8s column, nothing in the 4s column, something in the 2s column, and nothing in the 1s column. So 8, wow, that was really messy. 8 plus 2 is equal to 10. So nothing too advanced there. but it's just something you kind of have to see and understand. And there's a lot of little tiny rules, as I explained, to make it easier on yourself. Like, instead of having to, calculate each number by itself every time you need to know what it is in 10-base number system, you can just do what I said and say, well, that's in the 2s column, and there's, you can just add up the columns that way. So you have something in the 4s, I have something in the 2s, nothing in the 1s, I have something in the 8s, nothing in the 4s, nothing in the 2s, nothing in the 1s, and you can add them up that way to find the number much faster. So I'm going to stay on the same page here just because I have a lot of room up here. I'm going to switch to green just so you know I'm doing something else. So we've already established what we have for our binary system, at least the basics of it. We know how to count in binary at least, and we know how to convert at least for these basic numbers. It gets a little harder when you get to bigger numbers, but it's really just the same thing, just at a greater scale. And maybe you have to iterate upon it to actually get your final answer if you have a really big number. So for this case, what we're going to talk about is ANDing and ORing. I have something that's a value of 1 stored somewhere, and something a value of 0 stored somewhere else. So if I was to say I want to AND these two values together, what does 1 and 0 come out to be? Well, 1 is true, but 0 is false. Or 1 is on and 0 is off. So 1 and 0 comes out to false. So true and false comes out to false. So AND really says that we want both of them to be true. So ANDing 1 and 0 comes down to 0. Now for OR gates, let's say we have our same two numbers here, 1 and 0, stored somewhere in memory. And we're going to say, probably I broke my color scheme there. We're going to say we want 1 or 0. Now for this case, we have true or false. And what the OR is saying, it's saying that only one of them has to be true. So since one of them is true, then our answer is 1. We can say that, let's say we have our same two values. We're going to say we want 1 and 0. But in this case, we're actually going, so I'll put some parentheses around these so it becomes more clear. We're going to say 1 times 0. What is 1 times 0? Well, it's equal to 0. And then in our next case, we have, I'm going to do the same thing I just did, add some parentheses. We have our same two numbers, 1 and 0. And the way we represent an OR operation is a plus. So 1 plus 0 is equal to 1. And as you can see, we got the same answers, doing the same thing, just now we're representing in math instead of concepts. So here we're talking about conceptually, here we're describing the same exact thing mathematically. So in my next little bit of space here, I'm going to show you how we describe AND gates and OR gates in terms of symbols. So I guess I'll do some different numbers now just to mix it up. So I'm going to have 1 and 1 for the value, but we're actually not going to describe them with AND and ORs or times and pluses. We're going to describe them with logic gates, which really you can have an AND gate or an OR gate. It's really just the kind of physical model for the same conceptual idea. So we actually have electrical parts that can do things like AND two values together or two values together and other different things. There's a lot of other different things you can do with binary numbers, but this is kind of the basic building blocks. And so we have different representations of them, but the one for an AND gate is this kind of half circle shape thing. You'll see them drawn better online, so if you just type in AND gates online, you'll see different ones are the same. And the way we describe an OR gate is this kind of curly, pointy triangle thing. So the way that we do this, so I'm going to have these two numbers for the same. And so I have two inputs going into this OR gate. So that one's going to there, that one's going to there, that one's going to there. And what is our final value? So 1 and 1. Well, both of them are 1. So our output is going to be 1. And here we have 1 and 1. Now, in our mathematical model, this would be the same thing as saying 1 plus 1. But in binary system, we're not really doing it like actual math. It's still conceptual based. So even though we're using a mathematical model to describe it, it's still all conceptual. So 1 plus 1 in terms of AND gates and OR gates is still 1. So 1 or 1 is 1. Because it's just saying we want, one or the other. In this case, we have both, but it still is true that we have one or the other. So AND gates and OR gates just kind of put out zeros and ones for that. I mean, they don't know, but if we have a case like this, we're just doing 2 digits, we're only going to get out the same amount of that we put in. So if we were to OR 2 4-bit numbers together, we're going to get an output of a 4-bit number.